Development Program on quantum computing. We hope you have been enjoying this journey of exploration into the exciting intersection of quantum computing and artificial intelligence. The session premises to be particularly fascinating as we delve into the engineering challenges currently faced by developers of quantum computers. Quantum computing is a field filled with immense promise, but its development comes with unique and complex challenges. Understanding these hurdles is key to advancing this transformative technology. Our distinguished speaker for the session is Dr. Neeraj Kumar. Is an He is an assistant professor, grade second in the Department of Information Technology at Dr. B.R. Ambedkar National Institute of Technology, Jalandhar. He holds a PhD in Informative Technology with a specialization in IoT and AI from BBAU, Central University, Lucknow, and an MTech in IT with a focus on wireless communication and computing from Triple IT Allahabad, supported by an MHRD teaching assistantship. He also earned his BTech in Computer Science and Engineering from UPTU Lucknow. Dr. Neeraj has been a faculty member in the Department of Computer Science and Engineering at UPTU from 2006 to 2013. An accomplished researcher, he has published numerous papers in reputed international journals and conferences, including papers by IEEE and Springer, and authored over a dozen patents and books on advanced topics. His research interests encompass machine learning, computer vision, IoT, security, big data analytics, and soft computing, contributing significantly to these domains. Before we begin, we kindly request all the participants to keep their microphones muted to ensure a smooth session. If you have any questions, please type them in the chat box. We will address those questions during the Q&A session in the last. Without further ado, let us warmly welcome Dr. Neeraj Kumar. Over to you, sir. We welcome you.
Thank you, Kanika ji. Am I audible, Kanika?
Yes, sir.
Yes, sir.
Okay. I'm sharing window. Is it visible?
Yes, sir.
Yes, sir.
Okay. Today I'm going to actually discuss challenges that is faced by developers in quantum environment or in quantum computers, you can say. And this is actually an era where we are going to convert our technology from classical computers to quantum computers. That's why actually some problems facing uh, by the different developer at different stages. Initially, you can see it is a very simple things to show the challenges, but in case of computer or the quantum computing, it is little bit actually difficult because here hurdle actually coming uh, from its strong sides actually. Yeah? I think it is a fifth day of your workshop, and in which you have seen different uh, lecturers or the faculty members. Those already actually discussed six basic principle of quantum computing. I am today going to discuss the problems attached with these principles. Okay, because these are the problem those are facing by the developers. This is the uh, overview of our lecture introduction. Then we will go to fragility and decoherence. After it, data retrieval or the problem in the data retrieval. Fourth topic will be the errors. Next, quantum error correction. And next, software and hardware complexity. Then we will go to the conclusion. Is it visible, Kanika? Kanika ji, is it visible?
Yes, sir. Yes.
Okay, fine. These are the basically things by which actually we are going to discuss this. Mainly, quantum computers facing difficulty, or the developers facing difficulty in the quantum environment due to the nature of qubits. And what is the nature of qubits? You know, anybody can say me the nature of qubit? It is mentioned in this slide. Anybody? Is there anybody who can show me the nature of qubit, or provide me the answer to this very simple question mentioned in this particular slide? That is the sensitivity. Sensitivity is the nature of qubits that provides different hurdles to apply quantum computing in the computer science actually. So sensitivity actually provides problems at different principles or the mechanism already provided by quantum computing environment. First one is qubit implementation. Second, it interacts with the environment. So, and on the uh, connecting with the different parameters of environment. Next, superposition. You have already learned what is the superposition. But here, actually, you are going to see some problems given due to the superposition. Next, due to the gates. Next, due to the entanglement. Okay. Now, coming on the point of sensitivity. What is the sensitivity? It is the behavior of qubits. Okay, it is the behavior of qubits uh, after touching it from the different parameters of environment. Okay, any electron having two states, we know first one is a ground state and second one is a excited state. Okay, when electron moves from the ground state to excited state, then such kind of behavior called sensitivity. Such kind of behavior called sensitivity. It is the behavior of qubit, obviously, because it is depends on the electrons or the behavior of the electrons. Okay. So approximate 0 to it goes to 1. Yani it means from the uh, ground state to the excited state. Okay, when your qubit going to ground state to excited state, you just given them term as sensitivity. Next, why this sensitivity occurs? This sensitivity occurs due to the spin of an electron. Due to the spin of an electron. Okay, so here we have mentioned spin of an electron is the atomic energy level or oscillatory states in superconducting circuits. Okay, you can say inevitably it interacts with its environment, with particles, with magnetic field, with cosmic radiation, and then just convert its stage. Next, qubits are generally affected by some other parameters, or these parameters you may consider as a different kind of energy. Different kind of energy means thermal energy, electromagnetic field, mechanical vibrations, material impurities, and imperfect control signals. Okay, these different parameters just provides little bit disturbance, but those little bit disturbance just change the state or the simply quantum state of a qubit. Okay, quantum state of a particular qubit. Next, due to the changes in the quantum state of a qubit, it just uh, coming from the stable state to fragile state. Here you can see a little figure I have mentioned a figure where you are going to see just a fragile state and the stable state. When your electron or the qubit is in fragile state, figure will be shown just like a cat mentioned at the left hand side, and in stable state you can say your data, okay, in the stable state. So it is the basic problem of qubits due to the sensitivity. What is the problem? It is a fragility. It is a fragility. So you can say fragility is a extreme sensitivity behavior or the disturbance due to the sensitivity called the fragility. Okay. Quantum states are very delicate or easily distributed by their environment. That's why it leads to some kind of errors or some kind of another quality of your quantum bits, okay, or the qubits called, what we can say them, what is the effect of fragility? Is there anybody who can just mention it? Hmm? Is there nobody in chat box? Okay, no answer in chat box. Now, no answer in chat box. Okay, so that will be just actually I will show you in next slide. So give me answer at that time. Okay, sensitivity actually just provides some problems, and that problem known as fragility. Then fragility, if occurs in your quantum bits, then it leads to the decoherence that I have already mentioned in this particular page. Okay, fragility is a cause and decoherence is a effect. Okay, these are the effects of fragility, where actually effect of fragility you can see in the superposition, in the entanglement, in the environmental interaction. When you are seeing it in superposition, then your bits going to be collapse, bits going to be collapse, or the state going to be collapse. Okay, in case of entanglement, it is just an interaction, so it breaks the correlations. Okay, it breaks the correlations. When it breaks correlation, then called loss in entanglement. This loss also comes from the fragility. Okay, and third one is the environmental interaction. Environmental interaction. So at the time of when destroying the coherence, you are just assume that it is due to the fragility and due to the interaction of electrons environment with the environment or with the noise, any kind of noise. Okay, interaction will be performed at the level of different type of noise. Okay, it may be a electromagnetic field, maybe a vibration, maybe other kind of noise. Okay, or the temperature also. Okay, next, fragility. Next question is there anything by which you can maintain the fragility? हो सकती है नहीं? Is it possible or not? Yes, it is possible, and people just trying to do it, but right now it is not possible in current scenario. 100% actually you can't say it is a error free because due to the fragility. Next one is a decoherence that comes with the help of with the actually fragility. Okay, so um, when decoherence occurs, then you just assume that there is a something change in the superposition or in the entanglement. In the superposition or in the entanglement. In figure 3, you can see at the time of t, your quantum bits having the impact or the phase from one state, and at the time t dash it having the different phase. Okay, so it may be a phase change or maybe a bit change actually. That's why. Okay, it is a stage of superposition mentioned below. But when in this stage, actually a little bit change performed, then the coherence occurs. Or in second case, if something change in you can say coherence or coupling with others, then you can see the changes in the entanglement also. And when changes in superposition comes, then decoherence is started. Okay, next, it is a stages of superposition where you can say uh, equations. You can see the equation and the superposition principle mentioned in the particular figure. I think this slide you have already learned because it is a 50. So I'm not going in detail for this, but mentioned just to recap. I'm coming on the decoherence. When a qubit interacts with its environment, quantum information leaks. Okay, and qubit behaves just like a classical bits. In other words, you can say a qubit, when in isolated state, then it will be the stable state. It means it is not actually interacting with any other. Then it is stable. Just like a human behavior. If I am not attached with anybody or any surrounding, then my thoughts will be stable. In the same way, when qubits are isolated, stable quantum state occurs. On in another state, when environmental noise comes to me, then there will be a decoherence and classical behavior actually will be performed. Okay, someone can change my thought process and my state will be the uh, converted from the stable state to another state. Okay, in figure 5 you can see head tail just converted to the different stages actually can be converted. Okay, in one in two parts actually can be converted, or it is of two type. First one is a amplitude decoherence and second one is a phase decoherence. In amplitude decoherence, a bit flip performed, and in phase flip going to be performed. Okay, in figure 6 you can see this fact, bit flip and the phase flip. Okay, so ultimately bit flip and the phase flip are the two different reasons to be performed a particular decoherence of type amplitude or a type of phase. Okay, next, these are the differences between the amplitude decoherence and the phase decoherence. When energy going to be lost within the electron, then you can see initial state going to be just changed after the loss into the energy. And at that time, bit flip or bit flip error occurs, and it comes due to the different kind of noise. Here one noise I have just mentioned here, that is the thermal noise. Okay, so just stage you are seeing from 1 to 0, at that point actually amplitude decoherence occurs. Okay, at that time amplitude decoherence occurs. On the another set, you can see in the second figure, uh, where initial state just going to be changed due to the particular noise. In that case, just phase going to be changed. Here I have introduced the phase noise and phase flip error mentioned in this case. Okay, next. What is the relationship between the qubit fragility and decoherence that I have already actually stated before in one statement? You can see here sensitivity to noise in case of fragility and in case of hardware limitations. These will be the cause, okay, for the fragility. And what will be the effect? It will affect the decoherence, okay. It will just provide the decoherence as an effect of fragility of different type. If it is a sensitivity to noise, then loss of quantum state going to be performed. In case of hardware limitation, then computational limitation will occur. Okay, computational limitation will occur. For example, number of qubit actually may be increased, but we are not in the situation to increase the number of qubit in our circuit. Okay, that's why such kind of limitation called the hardware limitation or the computation limitation. Okay, fragility leads to decoherence, you can say. In this slide, I will ask you little bit questions and just provided the answer on the same slide, so you can imagine and just think about the answer. Okay, and a few questions I will ask you without the answer also. Here, which error affects the phase of a qubit? I have mentioned. Answer is phase flip error. Phase flip error. Next. Next one is a data retrieval problem. Data retrieval problem is facing by the developers of quantum computers. Okay. It is just coming from the different regions, but how information actually you are taking is a little bit tough task. It is not like a classical computers that we are using, because read, copy and paste here very easy, but in case of quantum computers it is not easy. Okay, and it is little bit heavy task, because RAM actually not working just like RAM actually not a concept in the quantum computer, but now people propose the solution uh, just like a RAM in simple computers as a QRAM, okay, or the quantum RAM concept of quantum RAM just proposed in this kind of actually scenario. You may see the scenario just like as when writing classical data onto QRAM, it will be forwarded to the quantum circuit. Okay. In another case, where when we are storing intermediate quantum data, okay, in QRAM, then you can retrieve it after the requirement, okay, when it required at the quantum circuit. So both scenario actually mentioned here, scenario 1 and scenario 2. It is a possible proposed solution actually. Why data retrieval is a problem? Why data retrieval is a problem? Because an n qubit register can represent to the number of 0 through 2 to the power n minus 1 simultaneously. Okay. Then it means for the long actually data retrieval, there will be some limitations to retrieve the data, and if we are not following our computation within that particular limit, then superposition just randomly collapse. Superposition just randomly collapsed, है ना? So it means 50 bit data. For the 50 bit data at the same time we require 50 bit actually qubits. Why actually it is a problem? There will be the three reasons. It is just hidden into the It is just hidden into the principles of quantum computing. Principle of quantum computing, you can see that is the no cloning theorem. No cloning theorem is a first, second one is a probabilistic output, and third one is a exponential state versus linear readout. You can say main villain in data retrieval is a no cloning theorem. No cloning theorem is a beneficial or the good for the cryptography purpose, for the security purpose in the quantum computers. But at the same time, it is just playing the role of villain for the database designers. Okay, why? Because it says unknown quantum state can't be copied. Okay, unknown quantum state can't be copied. Who says this? This is just a restriction given by the no cloning theorem. It means no backup of quantum data you can take, no duplication for verification you can actually have, because duplication not possible, and no read only copy for analysis available. Is it fine or not? Is there people who is understanding or not? Okay, parts. Okay, good. A little bit typical concept, but I'm trying to inform you in simpler way. Simpler way. Next one is a probabilistic output. Quantum algorithm actually don't have a deterministic output. Why? Because output is probabilistic. One run gives one random outcome. Okay, correct result appears only with some probability. It means retrieving useful data require what require? Repeated execution. Repeated execution required for the useful data retrieval. And second, statistical post processing. Okay. Third, classical computation after the measurement. Okay, these are the, so it means probabilistic output actually, when your machine providing probabilistic output, it is very good for the speed purpose. But if I want to retrieve the exact data, then you may require the different executions or the repeated executions. Okay, next one is a exponential state versus the linear readout. It is just lead to the mismatch. Okay, a system of n qubit stores information of 2 to the power n amplitude. Okay, measurement retrieves only n classical bits. Most quantum information is inaccessible by direct readout. Okay, inaccessible by direct readout. Direct आप नहीं कर सकते. Then next is a unstable data entanglement. What is the data entanglement? You have already, I think, learned about the entanglement. It is the ability of quantum systems to exhibit correlation between a state within a superposition. But when this correlation breaks, then we find out unstable entanglement. And at this time, what will be the consequences? Its consequences will be the data missing. Okay, so we can entangle the two qubits such that the measurement of one qubit is always correlated with the measurement of other qubit. But in case of unstable entanglement means correlation will be collapse, and at this time your one bit can't find the another bit, so data will be missing. It will be a chance. Okay, next next is a problems with gates. Okay, so quantum computing actually depends on the quantum circuit made by quantum gates, but it is different from the classical gates in terms of reversibility. In terms of reversibility, for example, when you are going to just mm, take some output from the NOT gate, in another case, when you are just putting the NOT gate to the output, it will provide you input. So it is the principle of reversibility. Okay, in case of classical gate, but in case of quantum gates, it is not guaranteed. It is not guaranteed. Quantum gate have higher error rate than classical gate, causing accumulation of error in long computation because it is not reversible. We require reversibility in the quantum gates. Okay, but it is always not reversible. It is not guarantee of the reversibility with the quantum gates. Second one is the gate fidelity and crosstalk. Quantum operations must be very precise. Okay, it should be actually far from the crosstalk because it increases error rates. And what is the impact of error rate? I'm just going to show you after this operations of qubits. Due to the nature of quantum physics, the destruction of information, you can see here quantum gates. You can see quantum gates here. So, what will happen? It is just you are seeing the AND gate here. We have put it some out input to the AND gate and getting output of uh, that particular AND gate, and you may find out different actually positions. Okay, after hiding one on the reversibility. On the other hand, in case of quantum gates, where gates are Hadamard gate, that is the uh, square root of NOT gate, you can say, or two different NOT gate arranged in particular order or in the sequence, you can say it is making a Hadamard gate. It just informing us that it should be reversible if you want to retrieve the data. Quantum gate are similar to the classical gate but do not have degenerate output. Their original input state can be derived from their output state uniquely. Okay, they must be reversible. They must be reversible. Another type of gate considered as a CN gate, that's a control NOT gate. Here you can see in the truth table, A and B are the two input, where B is a controlled, B is a controlled. So at this output side, you can see B is not changed, but A will be the change as per the position of 1, where in the control input in the B, you are seeing position 1, then just target will be changed. So 0 to 1 or 1 to 0, you can see in the output of the control gate, into the control gate. Okay, it is the position of uh, control gate. The CN gate has a similar behavior to the XOR gate with some extra information to make it reversible. It is possible to make it reversible with some extra information. Okay. Next. Next example actually mentioned here. That is the multiplication by 2. Multiplication by 2. Here you can see carry one bit, 0, 1, 0, 0, 0, 1. Then output will be 0, 0, 0, 1 converted to the 1, 0. Okay, in the same way, just it is going to be changed where 1 occurs. Okay. Next, here controlled NOT gate, that is the CCN gate mentioned here. When you are just going to see 3 input at there, bit on both of the control line. Here two control lines are there. Then target bit is inverted. Yani B and C mentioned here as a control and A is mentioned in the target line. Then in output you can see if two one available in the control line or in the B and C, then output of A output at the A will be changed from 0 to 1 and from 1 to 0. I think it is clear to all. I'm just want to see. Is it clear? Okay, fine. Next. A universal quantum computer also mentioned here. It is just works just like a NAND gate. You can see in the same way. You can see when our target input is 1, our target output is result of a NAND of B and C. Okay, you can see it in the table. You can see. Next, error percentage, error rate, error correction cost. Okay, these are the three different topics I have just considered for your actually knowledge. Little bit saying about it. In case of error percentage, what will be the percentage of error? Actually, you can see how much error in research we are just assumed. 95% accuracy if occurs, then we can say our result will be good or our research will be correct. Okay, so 5% left and right we assume as a correct. Okay, is it okay or not? Okay, but here actually 1% approximate in the thousand of one or the hundred, one from the hundred to one from the thousand, actually just assumed as a error. And what is the impact of that error? If I will assume as a 0.999 is correct out of 1, then error will be 0.0001. Then what will be the impact? Because process of is reversible here. I'm just showing that. Every operation performed on a qubit comes with a non-negligible probability of error. Okay. When quantum gate is applied, meaning an operation that transforms a quantum system from one state to another, the typical error rate is on the order of 10 to power minus 3 to 10 to power minus 4. Okay, 10 to minus power minus 3 to 10 to power minus 4. As a result, after roughly 1000 to 10,000 operation, the probability that at least one error has occurred become close to certainty. Is it clear or not? Okay, I'm not going Shore's algorithm right now or the Grover's algorithm actually just realize actually another things also and accuracy on that. But in that algorithms, you can using that algorithm actually a little bit it is reduced to 10 to power minus 9 to 10 to power minus 12. But initially actually not correct for all the operation. For all the operation, it is correct up to the 10 to power minus 3 to 10 to power minus 4. So error rate. Without an effective way to manage errors, quantum computing would therefore remain confined to small-scale experimental demonstration. Why for a small-scale experimental demonstration? Because it has little bit error, very little bit error, but this little bit error may lead to a big problem. Okay. Here in quantum computers, you can say quantum gates are imperfect, measurement are probabilistic, and qubit interacts with the noise. These are the three main reasons for the error rate. or the error increment in the error. Typical error rates are classical logic gates 10 to power minus 15 and quantum gate 10 to power minus 3 to 10 to power minus 2. This means one error in every 100 to 1000 operations. Is it clear or not? Is there any doubt? No. Next. Error accumulation very quickly. Quantum algorithms require many sequential gate operations. If a quantum circuit has 1000 gate, then error rate will be 1%, 0.1%, then error rate will be 0.1%. It means probability of error-free execution will be 0.999 out of 1000. It means approximately 0.37 will be the error. So 63% chance of failure occurs. 63 chance of failure occurs in particular operation. Okay. Next, error correction cost. Error correction cost. Quantum error correction required just to reduce the errors. Okay. High error rate, then more correction required, and more correction, then more qubit, and every qubit having its own cost. Okay, so number of qubit as per error rate, number of qubits as per error rate mentioned here in different scenario. Scenario number one, low error rate, and second one is a high error rate. Physical qubit per logical qubit, you can see low error for the low error rate 100 and a high error rate 10,000. Okay, physical qubit per logic qubit. Okay, these are the requirement. So ultimately, it is going to be very high cost. Why this is serious? Why error is serious? Because long algorithms always fail. In this case, deep circuits becomes unusable. Limit quantum algorithm execution due to the high error rate and restrict circuit depth. Few algorithms working here like Shor's algorithm, large scale quantum simulation, cryptography breaking. Okay, developers are forced to use short noisy algorithms only, but it is actually not possible for the long algorithms. Okay, for the long program or the number of operations we are. Next. Quantum noise, error correction, challenges, and scalability mentioned here in this section. You can see quantum noise. It is actually a phenomena occurred due to the fragile quantum state. Fragile quantum state. Okay. Quantum noise arises from the interaction with the environment. Interaction with the environment, and it may be created by the different parameters of environment and may create some problem actually due to it, that may be eliminated or may not be eliminated, so your information may be lost. Okay, then just to uh, save us from the missing information, we have to reduce the quantum noise. Error correction requires actually thousands of physical qubits. Because thousands of physical qubits required, then cost actually ultimately going to be very high. Okay, quantum error correction is built on principle. Which principle? Information should not be stored in a single qubit. Information shouldn't be stored. Instead of encoding computation in one physical qubit, the information is distributed across multiple physical qubits to form what is known as a logical qubit. Next, quantum error correction. What is the quantum error and what is the correction? To achieve fault tolerant computing, quantum error correction is essential. However, QEC require many physical qubits to encode a single logical qubit. ultimately it may be corrected with the quantum error correction codes. With the quantum error correction codes, it becomes possible to detect error with the help of quantum error correction codes, and then you can uh, try to another kind of method just to recover your data after the correcting or the correction codes after using the correction. Next, other probable solutions also actually tried by different developers. First one is a reinforcement learning or the quantum reinforcement learning, you can say. And second one is a auto encoder. Okay, at auto encoder. In case of reinforcement learning, classical control just goes to different agent that performs the action, and code deformation goes to data into quantum memory. Then this, after just performing some operation, it just send it to agent, and it will just uh, change your output after after the reversible process. It means one by one. Actually, after so many iterations, when you find out maximum accuracy, then you can take your data, or ultimately you can correct the code, you can say. Okay, so such kind of environment called the reinforcement learning or the quantum reinforcement learning. Another is autoencoder. Autoencoder, here you can see the neural network like architecture where one input is going to be collapse, and at that time we use the autoencoder, that is a circuit, and it is just uh, again create the same input, and then your error just going to be corrected. These are the basic concept just currently performed by the different researchers, those whose researches are just published in Nature in last year and this year also. Okay, in last of 2025. Next one is the scalability. Scalability is a power of quantum computers. It means you can add different qubit or different number of qubit with your circuit, but it is also at the same time it is also the problem. It is also the problem. So what kind of problem you see? Scalability in quantum computing is ability to increase the number of qubit, ultimately coherence and performance to solve complex and real world problems. So it is a basically a quality of quantum computers. But after adding some qubit, what will be the actually impact? It will just increases crosstalk. It just multiply the noise, and error rate rises further. That's why it is a problem of developers due to the scalability. It is the problem of developers due to the scalability. So high error rate is the main roadblock to the scaling, or the from hundreds to millions qubit you can't actually attach to find out good output at right now. Okay, scalability in another question I have put it here. Scalability in quantum computers is limited mainly by internet speed, software licenses, writing and heat dissipation, or the user interface. So answer will be C, wiring key problem. Next, what is the challenges of scalability? Scaling from hundreds to millions of qubit introduces problems related to the connectivity, wiring, and fabrications. So ultimately, scalability of quantum hardware, just limited qubit count, then connectivity and control, then diverse hardware platforms. Okay, in case of first limited qubit count, you can see uh, when you are going to scale up from 100 to 1000 qubits, then what will happen? it will just increase the number of crosstalks. Okay. And in case of connectivity and control, it just create heat. It will create the heat because number of qubit going to be high. So ultimately connections going to be increase. That's why heat will be introduced, and at that time, what will happen when heat comes into the circuit? Then what will happen? Circuit going to be fragile, electrons is going to be fragile, and at that time decoherence may occur. So we have to just contain the cryogenic environment. Okay. Another problem of scalability is diverse hardware platform. Different hardware platform available. Okay. Superconducting circuits, trapped icon, photonic qubits. Acha, related to this, actually one question also coming into the my mind. What is the scenario currently we have, or what is the era we are currently seeing? A superconducting circuit, trapped icon, photonic qubit, or other? Okay, it is an open question. You may find out the answer. Next, software or hardware complexity. Software or hardware complexity. Why software becomes harder? Why software becomes harder? Because error hide, algorithmic bugs, results are probabilistic and unreliable. Debugging is nearly impossible. So it is just providing your quantum computer hard for the software purposes. Okay. Next, it increases hardware and control complexity. High error rate force developers to add more control electronics. Okay. Increase calibration frequency, improve shielding and cooling, use complex feedback loop. And after increasing this, actually increment in system size occurs, power consumption occurs, heat generation occurs, and failure points also increases. And at that time, what will happen? Your electron going to be fragile and decoherence may occur. Okay, so it will be the problem for the developers. Okay, developers can't easily distinguish at this stage what is the hardware noise and what is the software logic error. Okay, user or the developer will be in confusion. He or she should change the hardware or should correct the hardware or just to check the bugs in the software. Okay, so it will be the big problem for the developers. Next, debugging quantum program is difficult because different conditions I have mentioned here. Programs are too large, qubit can't be copied or directly observed, lack of storage, slow processors. What is the answer? Is there anybody who can say me answer of this question? It is an open question. Is there anybody who can give me the answer for this question? Let us see one by one every option. Okay, debugging quantum program is difficult because program are too large. Is it you have seen the program is large in quantum computers? I think no. Okay, all the program you have learned will be not actually very big, or the algorithm is not very large algorithm, so it is actually not true. Second one is qubit can't be copied or directly observed. You have just seen this due to the no cloning. This no cloning due to the no cloning algorithm. Next option will be the lack of storage. Is there lack of storage? No, because it is working with the cloud. So no lack of storage. And fourth option, slow processor. Is the quantum processor slow? No, it is a very fast processor. So ultimately, you can see the answer B is correct. Okay. Now we we will go to the next slide. Software challenges and cost. Software challenges and the cost. It is lecture actually I have finished very fast. I think so. Uh, Quantum programming tools are immature and debugging is difficult due to quantum measurement constraint. Software challenges. Here you can see first one is quantum software immaturity. It means you have not developed till now a lot of algorithms like a classical computer you have developed. Okay, so ultimately software is immature. You don't have the compilers or the tools just to work with the quantum computers or creating the efficient coding. Okay, so error aware quantum programs are not available right now. That's why noisy hardware is a big problem and it is a non-trivial condition. Next, algorithm limitation. Obviously, you can see algorithm limitations here. You don't have a lot of algorithm like Grover algorithm or Shor's algorithm. We don't have a lot of algorithms here, so it is also a limitation. And I have just asked you one question in initial uh, realization time, which era you are feeling right now, and you will provide me the answer of this question. Which quantum era currently we are facing? Okay, just provide me the answer or just think about it. Okay, practical algorithm must be designed or adapted to work on noisy intermediate scale quantum machines or integrated with the classical quantum or classical computing and hybrid approaches also. Okay. Next one is a debugging and benchmarking. Debugging is also a problem. Why? Because developer don't know if this problem coming from the hardware or from the software side. So he is not able to try um, to correct hardware or to debug the software actually. Okay, he is not 100% sure from where it is the problem coming. Okay, if he has just performed the scalability. Next, what will be the cost? What will be the cost? High development cost, building, maintaining, operating quantum system. It will be a lot of, it take a lot of cost or it is a costly. In another case, you can use cryogenics or the cryogenic electronic cryogenic circuits. Why we require cryogenic circuit? Just to reduce our noise. Just to reduce noise, we require cryogenics. Okay, especially vacuum system, ultra fast control electronics drive up cost, and then you may see high development cost actually coming for the quantum computers or to the working on the quantum computers. Next, specialized infrastructure. Integrating quantum system into typical enterprise or data center environment is not yet feasible due to the actually infrastructure problem of infrastructure. Another is workforce shortage. Why workforce shortage? It is also the open question. Okay, I have mentioned here something, but you just assume that. Okay, or give me the question answer at the end. Why workforce shortage? There is a global shortage of engineers and developers trained in quantum hardware, software, system engineering, a bottleneck for the field of growth. So it is also a costly because workforce not available. But why it is not available? I'm just asking to you, and you can provide me the answer at the end. Next, control electronics. Control electronics. just refers to the classical controllers that must interact with the quantum hardware without introducing noise or the heat. One of the main challenge in quantum science is designing an architecture that solves the problem of massive interconnection, because a lot of interconnection actually occurs. Why occurs? Because you need to increase your qubits as per the operation, as per the requirement of operation. So massive data processing and heat load actually just going to be increases as you increase the different your what qubits in your circuit. Okay. In addition, part of electronic system must be able to operate in cryogenic environment. What do you mean by cryogenic environment? I will ask you. Yeah. Okay. You can give me answer, otherwise I will give you. Designing cryogenic electronics is the first things we have to just consider in control electronics. First is the processors and sensors. Processors and the sensors. Okay. That can actually work, can do work on different temperature or the room temperature at least. And second thing is it is the challenge to just use it on room temperature, on room temperature. So for electronics to be compatible with millions of qubit required beyond the current intermediate scale quantum computers, they must be able to operate at ultra cold temperature. Okay, ultra cold temperatures must be able, kindly note that they must be able to operate at ultra cold temperature. Okay. So just to put it on ultra cold temperature, we have required cryogenic or the cryogenic requirement or the cryogenic electronics requirement. Okay. What is the cryogenic requirement? Most quantum system operates at where? At what kind of temperature? At millikelvin temperature. At millikelvin temperature, requiring expensive and complex cooling systems, where you can see it is also the figure taken from a research paper, actually very good research paper published in December. Cryogenic and environmental requirement mentioned here: extreme cooling needs and environmental isolation. What do you mean by extreme cooling needs? Just understood it. Many qubit implementation must operate near absolute zero. Near absolute zero. Just function of a degree above minus 273 degrees centigrade. Minus 273 degrees centigrade, requiring complex and expensive dilution refrigerators and cooling infrastructure. So cooling actually a basic need of cryogenics environment. Second one is environmental isolation, shielding qubit from all external noise. All external noise means temperature change, electromagnetic interference, mechanical vibration, demands precision engineering and specialized facilities that is increasing our cost and obviously complexity. Okay, this is a chip actually made already by engineers, and it is able to uh, work at 12 millikelvin. Actually, you can see it is an optical image of cryogenic CMOS radio frequency multiplexer. Okay, next. Now, just think about the quantum computers, and I have a little bit question. In 2001, a 7 qubit machine was built and programmed to run Shor's algorithm to successfully factor 15. Shor's algorithm for successfully factor 15. Now, question is that can a quantum computer solve NP complete problem in polynomial time? Answer is yes or no. Obviously, no. That's why I have mentioned here. Okay. No. Why? Quantum computers can't solve NP complete in polynomial time because there will be the reason actually mentioned here. No known algorithm. Like Shor's algorithm for factoring, we have no algorithm for NP complete problems to be solved in polynomial time. So first reason is we don't have the algorithm for that. Second reason, black box lower bound. It has been mathematically shown that quantum computers can't give exponential speed up for NP complete problem using generic search. A lot of speed not possible always actually. That's why black box lower bound also a reason. And third one, if they could, then if a quantum computer solve NP complete problem in polynomial time, then what will happen? Then NP will belong to the BQP. Okay. Then quantum polynomial. Okay. Next, now we are on the conclusion. Actually, lecture going to be finished very fast, I think so, or something. Actually, it is not an interactive session. That's why it is finished fast. Quantum computing faces interdisciplinary engineering challenges that must be addressed to achieve fault tolerance, large scale systems. That's why you can see two concepts here. First one is a physical qubit and second one is a logical qubit. What is the physical qubit? Hardware implementation of qubit that is directly exposed to noise. And logically we assume that there will be noise or not noise. You can assume it. An abstract qubit constructed from multiple physical qubit and protected by error correction. You just assume it. So it is a logical qubit. The more physical qubit are used to build a logical qubit, the more reliable it becomes. Okay. In another case, you can see reduce different things or the increment in the qubit just actually provides usefulness here and useful after providing the usefulness we have to consider why it is not useful also. It is little bit less useful in the current scenario for the long operations. Okay, but we can ultimately overcome from those situations. Okay, uh, problem was only the higher error rate due to the fragile environment or the fragile nature of electron, but these are going to be solved due to the cryogenic electronics. Okay, it is going to be solved by the cryogenic electronics. So because of high error rates, results are noisy, reproducibility is low, and confidence in output is poor on the same time. That's why industry not actually utilizing it on drug discovery, financial modeling, optimization, cryptography. Okay. Next, these are the question I have just put it you as an open question. You can give me answer. First one is current quantum computer belong to which era? Second, which qubit technology operates at room temperature? Which technology? And third question, quantum error correction to difficult because A, it violates no cloning theorem. It requires classical encryption. It needs many physical qubit. It's slow classical computer. May I see the answers in chat box? Is there answer? No. NISA era. NISA era. Oh, 1B. NISC era. Okay, NISC era. Okay. It is correct. NISC era. is correct. It is correct. Sir, please display the question. Okay, 1 minute. Uh, just see the question. Now I can see the answer. One B, two photonic and two photonic. Two photonic is correct. And for third question, there is any answer? Okay. Is there any doubt if someone having? Then you may ask me the question. Pawan sir,
Yes, sir.
Kanika madam, you may ask me question if someone having. But
Yes, sir. Sure, sir. If any one of you have any questions, please ask them in chat box, or you can just directly ask the questions.
I think no question is there. Uh, uh,
Sir, I think there are no questions.
on another part, I'm just uh, inform you that if anybody interested to work with me on quantum computing, then you may work with me in NIT Jalandhar, actually notes or on online mode also, actually. Okay, I'm free to do work on the, but this actually on
Thank you,
the
sir. Thank you so much.
okay. Thank you, madam.
Thank you, sir, for this insightful and thought provoking session. Your discussion on the engineering challenges in quantum computing development has truly shed light on the hurdles and innovations driving this field forward. To our participants, we sincerely appreciate your attention and engagement throughout the session. Please don't forget to fill out the feedback form, which can be accessed through the chat or the WhatsApp group. That brings session 11 to a close. Once again, thank you, Dr. Neeraj Kumar, for your valuable time and knowledge.
Thank you, madam.
Thank you, all the participants, for your continued enthusiasm. We will see you in the next session. I request all the participants to wait for 5 to 10 minutes. Our session 12 will start soon. Good afternoon, everyone. It's wonderful to see you all again as we move into session 12 of our AICTE Training and Learning Atal Academy sponsored faculty development program on quantum computing. We hope you have been enjoying this transformative learning experience. This session is especially exciting as we focus on the practical applications of quantum machine learning. While we have explored the theoretical and foundational aspects of quantum machine learning, today's session will shine a spotlight on its real world applications across industries. Our esteemed speaker for this session is Dr. Vipin Balyan, a member of IEEE and an associate professor in the Department of Electrical, Electronics and Computer Engineering at the Cape Peninsula University of Technology, Bellville, South Africa. He serves as the program coordinator for the French South African Institute of Technology and the African Space Innovation Center. He holds a BE honors in Electronics and Communication Engineering from Dr. B.R. Ambedkar University, Agra, India in 2003, and MTech in Electronics and Networking Engineering from La Trobe University, Melbourne, Australia, and a PhD in Electronics and Communication Engineering from JUIT, Solon, India, where his thesis focused on efficient single code assignment in OVSF based WCDMA wireless networks. Dr. Balyan's research interests include CDMA, OFDM, 5G technologies, UAVs, fuel cells, and terrestrial and visible light communication. He has authored or co-authored over 100 SCI Scopus Index journals and conference papers and is a Y2 rated researcher by the National Research Foundation, South Africa. He has received numerous accolades, including the Departmental Teaching Excellence Award in 2022, the University Platinum Award for Research Publications, and the Bronze Award for the Postgraduate Supervision in 2021. In 2020, he earned the University Bronze Award for Research Publications. He has secured R1.8 million in funding from Hydrogen South Africa for his research endeavors. Dr. Balyan's professional profiles are accessible on platforms such as ResearchGate, Google Scholar, ORCID, and Scopus. His work and contributions significantly impact the fields of wireless communication and innovative engineering technologies. As always, we request all participants to keep their microphones muted during the session, and please feel free to ask any of the questions in the chat box and they will be addressed in the last of the session. With that, let us extend a warm welcome to Dr. Vipin Balyan. Dr. Balyan, we are honored to have you here. Over to you, sir.
Good afternoon, everyone. I assume that you are able to see my screen before I start
Yes.
saying something. Okay, and you're able to hear me also, obviously.
Welcome,
So,
Vipin sir.
yeah, thank you, Dr. Pavan. Yeah, you want to say something? Okay, so the thing is that when Dr. Singh, I'm not sure what's her name, Kanika Sharma was talking about me, I think it was the previous, I will say, my biography, which was read through. So I am currently working as a, can say, associate professor. That is correct. But I'm currently a C2
See,
rated researcher from NRF. So I was previously a young researcher rated. Now I am established researcher rated, which I got this year only. So that is just my brief change in my, can say, profile of biography. And with respect to number of research paper, I have now authored or co-authored more than 165 research papers. So that is about my, can say, profile, which I need to change. Can I just give me a second? Give me a second, why it's going to- Just give me a second. I just need to fixing my system. Yeah. So basically, the topic is practical applications of quantum machine learning, and as further going down to discriminative learning, and then we have unsupervised learning, which is a generative learning. What we are can say doing with respect to yes or no answers we usually have in terms of can say when we are talking about supervised learning or can say discriminative learning. So the usually the answers are basically in the form of yes and no, and then unsupervised learning is that you provide a data to the system of the computers, and then depending upon that the system generates a data which can be used for different applications as we go on. So example with respect to is that there's a face. So the question is there's a model, you provide an input with respect to a face, and you get an answer whether it's a face or not. So it's a yes or no. So this is one is your discriminative learning example of it, and then based on the data you use to train the computer or the device, depending upon that the can say the computer generates a face, and that face might can say generation of data, as you mentioned there that we have a generative learning. So it is what we call it unsupervised learning. So if we go further with respect to the classical computers, we provide an input with respect to it like 1 plus 1, you get the output with respect to it as 2. Cos pi you are providing, then answer may be minus 1. Yes or no. If you compare it with this, here also you are providing an input and you are getting an output. So basically, we have two types of computers. If we talk about today, we have classical computer systems also and we have quantum computers also. So in classical mode computers, you have an input, and with respect to it, you are getting an output. With respect to the quantum computers, there will be a generation of random numbers. So you will be providing the data, or based on the information provided by you to the computer will generate some random numbers, and depending upon that, you are getting an output. So the output is basically you are not providing the input to it every time. So it's generating the combination of it, and then it's giving you a particular output. So that is what your generative learning model is. So if we further go into detail of it, we have classical generative models and we have quantum generative models. So we have generative adversarial networks, GAN, restricted Boltzmann machine. We have variational autoencoder, VAE, and we talk about quantum generative models. Then we have basically quantum generative adversarial networks, QGAN, quantum Boltzmann machines. So it's basically see that same things are there, but the only difference is that we're replacing everywhere with a quantum uh, word there. And then with respect to quantum, then you have quantum circuit bound machines, which is abbreviated as QCBM. So the remainder of the can say lecture will be focused on this quantum circuit bound machines only. So all of us, we know what is a probability is. So that's basically how the data is generated and how you model it and which model you select depending upon the combination which you have is here I'm going to explain. So it's basically we have two coins, let's say, and we are tossing them. And when I'm saying coins, I'm considering them that they're not biased coins. So they are fair coins. So every time we are doing it, either it will provide us an input equals to heads or tails. It's not going to be like a can say mix of it. It's not going to stand. So it's not a unbiased coin. I will say it's an unbiased coin. Sorry. So let's say one model is there which will give us the probability of having head will be zero point 0.6. Another one is which will give us the probability of tails will be zero point 0.4. And then there is another model which is giving us heads as zero point 0.1 and tails as zero point 0.9. So looking at these model probabilities, we can clearly say that this one is unbiased coin because it's giving you more likely 50% probability for both of them. Okay, it might be the other way around also that one is for tail is zero point 0.6 and head is 0.5, 4.4. But this looks more fair or unbiased as compared to the why it's possible that there's a if you are tossing a coin, there will be head more less number of times as compared to tails. In a similar way, it's there, but it's basically that probability is the occurrence of something. So we are when we are tossing them, we are getting the results. Then we are 100% sure that it's going to happen. But when we are talking about probability or when we look at the probability theory, it's like how likely those events are going to happen. So obviously this model one is the winner moving we are generating a data which is basically we can say it will randomly generate data depending upon the probability you will provide to it. So it might be a different combination when we of head equals to zero point 0.6 and probability of tails will be equals to zero point 0.4. So it basically works in that way that you have a data which you provide to a model, and depending upon the data you provide to the model will generate the data, and it will be based on the data you are providing. So, like say we have this data, the pictures of three people, and one is a so we are sending this to the model, and depending upon that information of the data, the model is going to generate a data. So these are the two pictures of the people, can say that they are the actual peoples, and this is the data generated by the model, depending upon the information given to it. It will take a different combinations of them out of this data, and it will generate three images. Now, what goes into quantum is an important factor. So if we talk about uh, quantum is another, can say, one of the important application with respect to machine learning. So we are talking about quantum machine learning. So we need to know what is quantum bits, or the another name is qubits. So all of us know what is a classical bit is. The classical bit, you have two options only, on off, or you can say 0 and 1. So if we have a switch, we'll just press, let's say 0 is on the upper side and the 1 is on the lower side, means low and high. So if you are pressing the switch, so basically either we will be having a condition that we are not getting any output, or we are getting an output equals to high, or can say 1. But when we look at qubits or quantum bits, the thing is that there's a toggle there which will be moving between the different outputs. So it can be on the extreme sides, maybe on the this side and this side, but there's a possibility that there are combinations which are somewhere lying here also. So it is a possibility that you get one, sorry, 0 and 1, or you can say that it's 3/4 of 0 and 1/4 of 1. Okay, in a similar way, if I look at this side, we can see that 3/4 of 1 and 1/4 of 0. So depending upon the information which is given to the qubit can achieve any of the state. So the normal bits which the normal classical computers uses, it has only two states possible, 0 and 1. But with respect to it, there can be a combination of different states which are possible. And that's one of the important, can say, factor by which these qubit can be used to generate or can be used in future for many applications, especially because I work in satellite application field. So in satellite, it's very tricky to change the information. So if we can use, which I'm going to explain later also, that if we can have two bits which stays together for a longer time, and one is sent to the satellite, another one is in the ground station, and we can change the satellite in the ground station, automatically it will change the information in the another qubit which is in the satellite. So in that way, we don't have to send the transmit the information between the satellite links and the ground station. So with respect to qubit, so we have a term which we use as measurement. And the first thing is that this is on the form of a sphere, and the sphere is called as Bloch sphere or Bloch sphere, you can say, pronounce it in a different way. So we have these qubits are basically building block of quantum computers. So they operate on the basis of that. Okay. So qubit can goes to a north pole. We are talking about now considering it as a Earth. So this is a north pole, there's an equator, and then there's a south pole. So if it's this side, then basically you can say the value is equals to 0, and then when it's this side, it's equals to 1. So we can, when we look at it, we can see the probability of going to north and south is 50%. And when we look at these eyes are showing basically that we are measuring it or looking at it, and then we are able to find the information. So this is there's a possibility that these qubits are somewhere in this area. Then depending upon that, we can say that probability of north, I'm just mentioning the north here, or is 0.6 something, and the probability of south is, let's say, 0.4 something. So when we are saying that, let's say we assume that there is a magnet on them. So if it's close to this side, let's say we are saying the probability of it having in the north side is 0.7, and probability of it having on south side is 0.3. Now, qubit, when we use it to generate a model, so this can be linked to the events with respect to head and tails. So we can say it as 0.6 when it's in this area. If it's 0.4, it will be in this area. So depending upon the model which you are linking to it, so we can use, can say, uh, make our qubits prepare or learn according to the model on which we want to work. That we will see in the later slides also. So another experiment, let's say we talk about with respect to probability, and then we will bring it to qubits also, is that let's say we have 4 gloves and 2 of them are red and two of them are blue. And we are going to put them in the box here. And if we open the box and we want to look for a red, we can easily see that this is a red color. Then we are definitive that this gloves is of red color. But suppose I'm putting my right hand inside the gloves, inside the box, and I am managed to put so there are two gloves, two pair of gloves means there will be two left gloves, there will be two right gloves, and then there are two colors of gloves also, which is blue and red. So if I'm putting my hand inside it, and then without looking into it, maybe if I'm lucky with a 50% probability, I manage to get the right gloves in my hand. So by touching it, feeling it, I know that this is a right hand glove. Okay, but it's with the 50% probability. So it's a right hand. Suppose I'm looking for right hand blue. In a similar way, we can look a blue color and then we can enter our hand. So if we look at qubit, why this example is an important example? We look at qubit. Qubit has different bases, and when we say different bases, it's like that all of us have studied momentum and energy. When we are measuring momentum, we cannot measure on the same scale as we are measuring energy. So energy is like, say, we know the unit of energy is joules. So it will be measured on that scale only, with respect to that unit only. In a similar way for momentum, we know that momentum is your mass into velocity. So we need to have it on the basis of kilogram meter per second. So they have different bases. Or the can say, let's say a weighing system is there, then we are measuring them on a different weighing scale. In a similar way, when we are using qubit or quantum bits, then there are different bases for them. Now, let's say I assume that uh, the North Pole is considered to be my having red color gloves on the top. I forgot to put that one there. And the bottom is the blue color one gloves. And the probability of having a right hand gloves, it can be a red or a blue, is on the right side, or can say shown by a green color here, green color base. And left hand gloves, or can be of any color, is shown by this. So this is positive, negative. So we have different bases. When we are looking at the colors of the gloves, we have bases as this axis, which is north and south pole. When we are looking at the hand, then we have different axes, which is your x-axis with respect to this sphere currently. So we have a positive and negative. So depending upon how we want to use our qubit for an application, then we need to have different bases for that. It's a most important basis for measurement will be, you can say, Z basis, which is your north and south poles. Then you have X basis, which is your negative and positive, and then there will be a plus I and minus I. And this is basically Y basis, and it is used for complex numbers. When we are doing quantum computing, or then we use this basis very frequently because complex numbers are also there. Okay, so now your bits and qubits and gates. So classical computers, all of us know that we have bits as 0 and 1, and we have a logical gates, which are like AND gate, NOT gate, OR gate, or XOR, or maybe a XNOR, but they are again the combination of these basic gates, I will say. So, but with respect to quantum computing, we have rotation gates and you have entangling gates. And this is the most important application of quantum entangling. That's the term which I was uh, talking about when I was talking about satellite communication. So rotation gate is that you have some place where your this information is placed or the location of this, and then you want to rotate it with respect to Rx, you want to rotate it with respect to Ry, where your Rx, Ry, Rz are these bases. These bases, how you are doing it. Okay, and then you have entangling with this XX, XY, and ZZ. So how to get qubit into right position? Suppose you want to send the information and the position of this qubit is on the north pole and you want to rotate it, then you bring a rotation gate. So let's say we have a position now as 0 there, but you want to change it to some other value, let's say 0.6 or something. We need to use a rotation gate which will bring this to this point on the Bloch sphere. Okay, and these are your quantum rotation gates. So this is your Y, your Z, and your X. These are same with respect to looking at it. So this is basically when you are rotating Rx around your x-axis. This is the theta angle by which you are rotating it. So it's turning like this. And then you have Ry theta, which is passing through this line. And you are rotating the Bloch sphere around it. Or you are basically not rotating a Bloch sphere, I will say. You are rotating your qubit with respect to this y-axis. So this is the angle theta by which we are rotating it here. And then you have z axis, which is your this theta angle which we are rotating, and this is your z axis. So with respect to this, suppose you want to generate input is given to you. You use a y theta, this one. And initially, you want to generate a model which will give you 50% of heads and 50% of tail. So 0 is considered as your north pole. So it will be considered at this point, and 1 will be considered at this point as tail. So you will have, I'm not able to show the another one, but there will be another qubit also. One qubit will be used, and then using it will be on north pole. Let's say it will be here, and then these two qubits will entangle to each other, and then one of the qubits will be rotated by in a way around the y-axis that it reaches this point. So then there will be, so you will start with the qubit on the north pole, and then you will rotate it by y-axis, and then you have this qubit which is sitting down here. Okay. Then if we talk about simulation with respect to a biasing of a coin toss, again the same thing, head and tail, but you now want to make it 60% and 40%. So you will rotate again by y-axis and you will move it to slightly to this position. So one of them will be like probability of 60% and another one will be a probability of 40%. So if you look at the problem in this way, suppose we have two coins, one is a round one, another one is a square, and you want to have this data which you want to generate. So it is, if you look at it, there is a 50% probability of this combination, sorry, 25% probability of this combination, and 25% probability of this combination, and so on for these four combinations. And we are using a coin. So each coin is considered to be unbiased coin or can say fair coin. So the head and tail has the probability 0.5. So we can say 0.5 into 0.5, 0.5 into 0.5 because head and tails are equally likely in a coin toss. And we have two coins. Sorry, we have model 1, which is generating zero point 0.5, zero point 0.5, coin 2 again generating 0.5, zero point 0.5. So then this combination will form. So this is with respect to another problem if we take is that we have a head again, but now the probability of having this first uh, event is higher, 72%. Second one is 18%. Third one is 8 and then 2. So this will be zero point 0.9 into 8, or it can be zero point 0.8 into zero point 0.9, depending upon how you are using these probabilities here. And then it will be zero point 0.9 into zero point 0.2, zero point 0.1 into zero point 0.8, zero point 0.1 into zero point 0.2. So then you will have uh, XY combination with respect to it like this. And in a similar way, you need to uh, train your these qubits. You need to move them in a way. Earlier we were using the only one coin, but in a similar way you have to use a combination of two coins now, which will generate us the information in this way. So this there will be a RY, and we are rotating one with respect to angle theta one, and then there will be another RY, or can say rotational gate. RY and RX represent here rotational gate. So one of them will be rotating at an angle theta one, another one will be rotating at angle theta two. Okay, then this is the measure by which you want to do it. Sorry, I forgot to mention that one. And depending upon how you are rotating, there will be a position of your qubit. Okay, so if qubit is here, then it's head. If qubit is here, then it's tail. So depending upon how you are using two combinations, you will generate the data in this way. Now, quantum entanglement, which is an important property of quantum. So this is maybe the future. Uh, we are working. One of my PhD student is working especially on this entanglement. We managed to do certain things in the, can say, in the lab, but obviously we are not able to achieve what we are planning. We were planning to achieve currently. Hopefully in the future we will be able to achieve it. We have a satellite group also in the university, and we managed to launch two ZAQ satellites from there. And what's the, can say, future plan is that if we can use this quantum entanglement to transfer the information from the ground to the satellite, but which will resolve many problems, because what will happen is that if we brought these two sphere together and we keep them so close to each other for a longer period of time, that if we separate them even by, we'll see the billions of years also, distance also, then if we change one, it must be able to change the information to another one. And let's say one is on the ground station, another one is on the satellite. So if we change the information, let's say I change from 0 to 1 on the one in the ground station, then it must automatically change the information in the other qubit. So we have these two quantum bits which were kept together for a long time. Now they are separated by billions of light years distance, we are talking about. And then if you change the information in one, it must be able to change the information in another one. So we have, can say, different levels of entanglement. So let's say 25%, sorry, not entangled, and a little entangled, more entangled, and totally entangled file state. So in this one, the again everything here is explained with respect to now currently the head and tail combination. So head and tail, if we are tossing two coins, we can have only four combinations. Depending currently here, depending upon that, everything has been explained. You can use a case of tossing three coins also. You can take a case of tossing four coins also, or depending upon which type of model you want to build. You can take a case with respect to the bits. The best example, you take a 2-bit, 4-bit scenario, 8-bit scenario, or 16-bit scenario. Okay. So if they are a little entangled, depending upon how they are entangled, so it's 30% of both having high, or can say on the north pole, I will say, will be there. If more entangled, then it will this will go 40%, this will go 40%, and this portion will form only 10%, which is like one of them is red, another one is with respect to we are talking about here. So can say one is head, one is tail. That is the uh, as we go up on this side, on the from move from 0 to pi, we will say, then we are basically going towards having the higher probability of one type of output, either heads or either tails. Okay, so this is the combination. Let's say we have a uh, four toss of the coins. Okay, and the 4 coins are there to toss, and we are tossing them 16 times. So as we make it more and more tangled with each other, entangled to each other, the probability of this will increase up to 50%, 50%. You can say the four of them must be head, or four of them must be tail. Okay, so we use these gates, which are Molmer Sorensen gates, for this purpose and for the same purpose. So to get 50%, 50%, and these gates provides us this power output as 50% of this combination, 50% of this combination, and the remaining combination turned out to be 0. Okay, so depending upon what type of where application we are using these qubits, and again when we are using qubits, we are using your rotational gates also, and different ones of these ZZRXX, YY entangled circuit also then we are using. So this is basically a RY, rotation by Y, RY. Then you have a rotation with respect to RZ, then rotation with respect to Y. And then if you see ZZ is used there, and then it's getting connected to this one. So whatever the input on this one will be, the output of this will be, it will be going to this one also. This is what this connection shows, that from this it's connected to this, and they are going, we are having four combinations on this side, four qubits we have on this side, and depending upon how we are rotating, what different combination of entanglement we are doing, we are receiving, we are going to measure the outputs. Okay, then we have different architectures in which again we can apply your entanglement and these quantum machine learning circuits, is that we have star topology. People from computer science are better, can say, aware of these topologies as compared to me also, I will say. So star topology, then line topology is there, and fault topology, which is a combination of it. Star topology is there that you start from this side, and as you are going on to this side, you can see that these are, the second one is depending on the first one, and the third one is depending upon these two, whatever the combination is there, and then the fourth one is depending upon them. This. So then you have line topology, so it's going sequentially. So whatever is coming to this side, it's going to this. So star is basically, you can say, there are three circuits here, then they are connected to the first one is connected to the second one. The second one is connected to the third one. Third one is connected to the third of this is connected to the fourth qubit, which is coming on this side. In the line topology, it's coming like this, that this first one is connected to the second one, this block, and then it's going into the input of this block, and basically going in a line like this. And then this is a combination of all the topologies together. Okay, so if we have this, suppose something is given to us and we want to fix it, so we can use as many as combination of these rotational circuits depending upon what are the requirements to us. Let's say we want to fix it with respect to y axis and z axis only. We can use a different combination, different angle combination also to fix the different qubits. So here, suppose we are changing it by an angle theta 9. We are using the sequence so that we know that which angle we are talking about. The same, let's say we are applying here. So if we are using the first technology, which is your star topology, then it's going there, then this one is going here, and then we can measure them. Quantum circuit bound machines, so we can use them in the form of layers also. So this is the layered structure. So you have first layer, the output of which is going to the second layer, the output of which is going to the third layer, and they are not limited to this point only. So this can be further progressed with respect to the number of layers which we are using. The goal is ultimately to use this combination in a way that we have this probability of these two in the maximum value and the remaining at minimum, because the, if these qubits are not entangled properly, then the output which you will be receiving on the other side will not will be with errors. So if they are highly on one side, or can say you have only two outputs possibilities, then it's better to decide with respect to the circuits what we are using different applications. How to train these models? So, like say flipping of the coin, if we look at it, generally they have equal probabilities. Okay, so we will provide the data in a way that they have equal probabilities. But when we are designing the circuits, when we are applying it, we will be using the different combinations of your rotational gates and entanglement circuits, which can provide us the desired combination of entanglement that is close to 50%, not exactly. With respect to the bars and strips data sets, the data will be in this form, so we can provide the information to the I can say the data set which we are providing. We can provide it in this form, which which can lead for us to have the maximum probability of everything. This is another way of looking at it. And this is again coming back to what is quantum and machine learning. Sorry, uh, before going into it, the applications where we are using them now with respect to the actual, as I explained to you, we are going to use it for satellite communication. And satellite communication is this qubits are gaining too much attention. All over the world, people are doing research on it because when we are setting up communication between a ground station and a satellite, we have to spend a lot of amount of money on transmitting antennas and receiving antennas. But when we have a qubit which can help us in changing the information. Suppose I have four qubits and I want to tell to satellite that instead of number two, it's number three. So I will just change only one bit or two bits of combination. So my two is for with respect to four bit is 0010 and three is 0011. So I will just change my last bit, or can say qubit, and it will be able to change the information on the other side. So then this whole problem of can say qubits uh, but the thing is that how we can implement it successfully on the existing satellites, because their onboard computers are not ready to, can say, accept the information in the form of qubit. So we need to make their onboard computers also, which are uh, like quantum computers, which works on qubits, and there must be a way by which they must be able to work on both sides, on the computer information also, and quantum computer information also. So that is more of can say overview with respect to the application of it. I just touch only one application because I am aware of this one. So, but there might be another application on which we can use this quantum machine learning. So, if you have any questions, please go ahead. Thank you.
Thank you so much, sir. Do you have any doubts, all the participants? If you have any doubts, please do ask.
Yeah, I can provide my email address to you, on which, if you want to get some, I will find out some research paper for you, which is with respect to quantum computing, and soon we are working on it. Maybe we'll be.
Thank you so much, Dr. Vipin Balyan, for such an engaging and enlightening session. Your insights into the practical applications of quantum machine learning have truly opened our eyes to the immense potential of this field in revolutionizing various industries. From quantum driven advancements in healthcare and finance to the optimization of transportation networks, your examples demonstrated the profound impact quantum machine learning is already having. We deeply appreciate the clarity and depth of your presentation, sir. To our participants, we hope you found this session valuable and inspiring. Do not forget to fill out the feedback form, which has been shared in the chat and WhatsApp group. This concludes session 12. A big thank you to Dr. Vipin Balyan for your invaluable contributions and to all the participants for your active participation. Stay tuned for the next session as we continue to unravel the world of quantum machine learning. See you soon.
You, but I was mute too. Thank you.
Thank you so much, sir. I request all the participants to wait for 5 to 10 minutes before we proceed for next session.
Participants, next session will start from 4:45 p.m.
गुड आफ्टरनून पवन सर.
जी सर.
हेलो.
Yes, sir.
सर ये अभी कितने बजे तक चलेगा?
Around 6 p.m.
6 p.m. ओके सर।
Yes, sure, ma'am, you can leave, but please join before 4:45.
4:30.
4:30, ma'am. Okay, sorry, sir. Chand. Good evening, everyone. As we arrive at the concluding session of our AICTE Training and Learning, Atal, Academy sponsored faculty development program on quantum computing, we are thrilled to welcome you all to session 13. The final session focuses on an incredibly thought provoking topic: future trends and challenges in quantum computing. It's an opportunity to explore the cutting edge advancements shaping the future of quantum computing and to discuss the challenges that lie ahead as we continue to innovate in this fascinating domain. To guide us through the insightful journey, we are privileged to have with us Dr. Amit Singhal. Dr. Singhal is a distinguished academician and researcher currently serving as professor and head Department of Computer Science and Engineering at Rajkumar Goel Institute of Technology, Ghaziabad, Uttar Pradesh, India. With nearly 24 years of rich academic experience, he has made noteworthy contributions to teaching, research, academic administration, and leadership. He is a senior member of IEEE USA and the Asia Society of Researchers ASR, life member of several esteemed professional bodies including ISTE India, IEEE Computer Society USA, CSTA New York, IACSIT Singapore, IAENG Hong Kong, Internet Society, ICST Belgium, IFERP, and many other national and international technical organizations. Dr. Singhal has authored more than 70 research publications in reputed SCI Scopus Index international and national journals and conferences. He has also published multiple academic books, particularly in the areas of cloud security and cloud computing, providing valuable resources for researchers, academicians, and industry professionals. He actively contributes to the global research ecosystem as an editor and reviewer for leading journals, including those published by IEEE and Elsevier. Dr. Singhal has delivered numerous invited expert lectures, chaired technical sessions, and played key academic and organizational roles in international conferences and academic forums. His academic excellence and innovative teaching practices have been widely recognized through several prestigious awards, including the Teacher Innovation Award by the Sri Eurobindo Society for promoting joyful and experiential learning, BEST SPOSC Award by Professor Bhaskar Rammurthy, Chairman NPTEL PIC and Director IIT Madras, Academic Excellence Award, Vishisht Shikshak Samman, and the Maulana Abdul Kalam Azad Excellence Award of Education. Without further ado, let's give a virtual round of applause to Dr. Amit Singhal. We are honored to have you here, sir. Over to you, sir.
Thank you, Kanika. Thank you so much. Just give me 2 to 3 minutes only to connect with me because of the electricity problem.
Okay, sure, sir.
Okay. Right now I'm at my home and there is some problem. So only 2 to 3 minutes, please.
Participants, please wait for 1 or 2 minutes.
Hello,
Yes, sir.
हाँ जी.
am
Yes
I
sir.
audible?
Yes sir.
Kanika, my screen has been shared or not
Yes
properly?
sir. Yeah, yes.
It is visible to all? Hmm?
Yes, sir.
Yes sir. Screen is visible.
Okay. Okay, thank you. So, good afternoon, all, and I welcome you all for this AICT Atal FDP on quantum computing. As we aware that, am I audible now? Just I'm confirming.
Yes
Yes,
sir.
sir.
Yes sir.
Thank you once again. So, as we aware that the quantum computing is a new and powerful way of computing that uses the principles of quantum physics to solve problems that are very difficult or even impossible for today's classical computers. So, over the past 5 days of this AICT Atal FDP, we have learned about the quantum computing and from multiple important dimensions, you can say. So we discussed its basic ideas, how quantum information works and quantum computing is used, its role in the large language models, quantum cryptography, cyber security, so and different quantum tools also. And for today, my topic is the challenges and future scope of the quantum computing. So my presentation talks about the major challenges faced by current quantum computers, such as unstable hardware and error in calculations. And these challenges place today's systems in what is called the noisy immediate scale quantum, that is NISQ era. At the same time, it highlights the huge future potential of the quantum computing. So,
So please your PPT in full screen mode.
okay. It is not visible.
Sir,
The text is not visible.
visible but not. Some participants ask to share in full
Okay.
screen.
Okay. Just a minute. Now it is visible.
Yes, it's okay.
It's okay now.
Yes, sir.
Okay. Thank you. So the classical computer works using the binary bits, as many of the speakers have told since last 5 days, and perform tasks step by step. So their performance mainly improves by adding more hardware. So quantum computers, on the other hand, using uses the qubits, which can be both 0 and 1 at the same time. Simultaneously, we can use both of them. So this allows them to process many possibilities simultaneously using special quantum effects like superposition, entanglements, and interference. Quantum computers can search through multiple solutions at once. So, because of this, quantum computing does not just make computers slightly faster. So, it has a potential to be much faster for certain problems. This could be greatly change how we solve complex tasks in areas such as optimization, scientific simulations, and material sciences. So this is the historical milestones that I think it is already discussed in the last uh, few sessions. That is started with the Fiance visions, Reusse model, Short's algorithm, Grover search, and uh, in the current era, today's countries and companies around the world are investing heavily in quantum computing, and the goal is to achieve quantum advantage, where computers solve real problems better than classical ones, and turning theory into practical and life changing theory. So next is the fundamental quantum principles. So quantum computing works because of four main ideas, that is superposition, that is the qubits exist in that can be 0 and 1 simultaneously. Entanglements, I have heard about the in the last the second last session of the day, entanglement in the detail. Interference and the measurement also, when we check the result, the quantum state turns into the normal value 0 and 1, and the answer we get is based on the probability. There is no single best type of the qubit yet, and different technologies have different strength and weaknesses also. So supercoding, so superconducting qubits are very fast, but need extremely low temperature. If we talk about the trapped ions, that is qubits are very stable and accurate, but their operations are slower. If we talk about photonic qubits, they can work at room temperature, but it is hard to scale them to large systems. And the last, neutral atom qubits can connect many qubits easily and are promising for the large systems. So each methods involve a trade-off between stability, accuracy, speed, connectivity, and ability to scale up. So this healthy competition is pushing researchers toward building reliable, large-scale quantum computers in the future. Just I'm comparing all the qubits because of its pros and cons also. This is the right now we are in the noisy intermediate scale quantum NISQ era. So this means today's quantum computers have 50 to 100 qubits, but these qubits are not perfect and cannot fully correct their own errors. So because of this, current machines have many problems. Uh, Errors happening often. Qubits loss information quickly, and there are not enough qubits to run most useful quantum programs. So, to make progress, scientists combine quantum and classical computers, where classical systems help control, correct, and optimize the quantum parts. So, even with its limit, the NISQ era is very important. So, it acts as a bridge between the today's early quantum machines and the future quantum computer that will be stable, reliable, and powerful. Some important quantum algorithms show how powerful quantum computing is. So, Shor's algorithm can break today's common encryption method much faster than classical computers. Grover algorithms searches the database faster than the classical search methods. Just I'm comparing with the other ones so that a simple overview can be given to all the participants of this FDP. And that is quantum approximate optimization algorithm is designed to solve um, complex optimization problem and can work on today's early quantum machines. And last, VQE, that is variational quantum eigensolver, and HHL algorithms are useful for chemistry simulations and solving mathematical equations also. So although we these algorithms are very powerful in theory, and most of them need large error-free quantum computers with millions of the qubits. So today's noisy quantum devices are still too small, but they are an important step towards that future. The quantum computing has a potential to change many fields in a big way. So in security, it can create extremely secure communication and also requires a new encryption method that can resist quantum attacks. In drug discovery, it can help scientists better understand how molecules behave, leading to faster and more accurate medicine development. In finance, it can improve investment planning and risk analysis. In supply chains, it can optimize routes and logistics, saving time and cost. In machine learning, the quantum computers may recognize patterns faster. In climate science, they can build better models to study climate change and sustainability. Overall, the quantum computing is a powerful general technology that could bring major changes across many industries. So next is the critical challenges and future outlook. Quantum computing still faces many big challenges. To fix errors, we need thousands of the real qubits just to make one reliable qubit. So building systems with millions of the qubits is very hard and require major advances in hardware control and extreme cooling technology. So we also need new ways of programming and new algorithms that work well with quantum hardwares. So, in addition, there is a shortage of trained experts. So, skill from physics, computer science, and engineering must come together. This slide introduces the major hurdles in building useful quantum computers. My next slide, that is the uh, overcoming and challenges. So this path forward is filled with complex technical obstacle that must be navigated. And building useful quantum computers is difficult because many problems are connected to each other, and qubits are very sensitive, and even small changes in the environment can disturb them and cause errors. So these errors happen much more often than if we compared with the normal computers. So making quantum computers bigger is also hard as we add more qubits controlling them, and all at the same time simultaneously, we can say that becomes it becomes very complex. And on top of this, the software for the quantum computers is still new, and the technology is expensive, and there are not enough trained experts And to overcome these challenges, scientists and engineers from different fields, physics, engineers, and computer science, must work together and continue innovating. Quantum computer hardware works under very extreme conditions, and the qubits are the extremely delicate and usually need very low temperatures, close to absolute zero, so that heat and noise don't disturb them. And making qubits that work accurately and can connect well with each other is very difficult. So, because of this high sensitivity, building stable and large scale quantum computers is one of the biggest engineering challenge in quantum computing. Decoherence means losing quantum information, and it is one of the biggest problem in the quantum computing. And qubits are always affected by their surroundings, such as heat, electromagnetic noise, which disturbs their quantum states. So errors also happens because of control signals used to operate qubits are not perfect. So as a program runs longer, these error build up, and the it reduces the accuracy. And to reduce this problem, scientists use better shielding and special techniques to protect qubits. But this makes systems more expensive and complex. And increasing the time qubits can stay stable is very important for running useful and meaningful quantum programs. In this slide, I'm showing the high error rates and the gate fidelity. And today's quantum operations still make many mistakes. Each quantum gate has an error rate of about 0.1%, which is much higher than the error rate in the normal computer circuits. So while this error seems small, it adds up quickly when many operations are performed, making long calculations unreliable. And to build reliable quantum computers, we need accuracy of more than 99.9%, which has not yet been achieved on a large scale. So errors can also happen when measuring the final results. Because of this, the researchers are working hard on better calibration, reduction techniques, and more stable gate designs to reduce these errors to acceptable levels. Next is the scalability challenges. Increasing quantum computers from a few dozen qubits to millions of qubits is extremely hard, and controlling many qubits at the same time without them interfering with each other is a big challenge today. So as systems grow, the control uh, electronics, wiring, and measurements devices also need to grow. But this often adds more noise and errors. And one possible solution is to build smaller quantum processors and connect them together instead of making one huge machine. So even then, problems like manufacturing quality, limited physical space, and the need for very large cooling systems make building reliable large quantum computers very difficult. So quantum computing software is still in an we can say it is in the early stage. Wiring and debugging programs often requires strong knowledge of the physics, and tools are not yet user friendly. So the technology is also very expensive. Quantum computers need special cooling systems and advanced labs, which cost a lot to build and maintain. So because of this, only big companies and government can afford them right now. So there is also a shortage of the skilled peoples who understand both quantum physics and computing. While if we talk about cloud, we if we access the clouds to quantum computers, and better education programs are helping more people. It learns and experiments and making quantum computing affordable and widely available with that will still take several years. To solve these problems, just we are discussing here the main problems, challenges of the quantum computing. So to solve these problems, we need continuous teamwork and innovation. Why I said teamwork? This includes making quantum hardware more reliable, improving error correction methods, and creating easier to use software. Collaboration between universities, companies, and governments is very important. That's why I asked about the teamwork. And each challenge is also an opportunity for the for any breakthrough. So, with ongoing research, better education, and stronger infrastructure, quantum computing can move from being a lab experiment to a powerful technology that changes the way we solve problems and use computers. So, next is the quantum security challenges. So, these quantum computing presents a dual-edged sword for the security, and this quantum computing affects security in two ways: positive side, negative side. Always we have these two uh, sides. That if we talk about the positive sides, it can create extremely secure communication using QKD, means quantum key distribution. Negative side, it can also break today's common encryption like RSA, because algorithms such as shores can decrypt data much faster than the classical computer. So this means sensitive information that could be stolen now and decrypted later, creating a serious security risk. And to stay safe, we need to move to post quantum cryptography, which can resist quantum attacks. So, government and the organizations must invest and plan ahead to protect the security, finance, and the public trust. My next slide is about the transformative horizon. The quantum computing is on the path to a big changes, and hardware is steadily improving, giving more stable and controllable qubits. And new algorithms and software are being developed specifically for the quantum machines. Worldwide collaborations and the large investments are the speeding up the progress. And hybrid systems that combine quantum and the classical computers are already showing benefits today. So in the long run, quantum computing could revolutionize the science, revolutionize the science and industry, we can say. And it helps us to discover new material, improving climate models, and to solve the problems that is related to the classical computers. And the potential gain for outweigh the current challenges also. In the next few years, we can expect the better NISQ devices with less noise and longer qubits stability, allowing more advanced hybrid quantum classical algorithms. Quantum cloud platform will make it easier for more people to access and experiment with quantum computers. So early commercial applications in the area like different areas like finance, the logistics, that showing the real world benefits. So improved software tools and the education programs helping train more experts to push quantum computing towards larger and more powerful systems. In the next 5 to 10 years, quantum computing will move from experiments to the practical use. The first error corrected qubits will allow reliable computation for a specific task, and the system will scale up to include more qubits. Standard tools for framework will make it easier to combine uh, quantum and classical supercomputers. Quantum communication network will expand, improving secure data transfer. As these challenges are overcome, more industries will start using quantum computing. Access will become cheaper, and the global collaboration will grow, making quantum computing a key technology for the future. In the long run, we expect fully reliable quantum computers with millions of the qubits that can run complex algorithms every day. They will revolutionize AI and make all encryption quantum safe. And the scientific discoveries in physics, chemistry, and materials will happen much faster. So, quantum computers will become widely used, supported by clear ethical and legal rules. And this is not just a small improvement. If we think about it, it is not just a small improvement, it will completely change how we solve problems in science, industry, and technology. My next slide is the quantum secured future. So the quantum computing is changing the way we secure information. So classical encryption could be broken by quantum computers. Quantum key distribution can create completely secure communication. So new post quantum cryptography standards are being developed worldwide to replace current encryption. The government and banks are investing heavily to protect sensitive data for the future. And this proactive effort is essential to make sure our digital system remains safe in the coming quantum era for the future use. Next slide shows the revolutionize in the field of the healthcare and AI. The quantum computing could bring major advances in medical and artificial intelligence also. If we talk about medicine, it can simulate how molecules interact and helping discover new drugs faster and design personalized treatment for the severe diseases like cancer also. And in AI, quantum computers can handle large complex data more efficiently, creating smarter and faster machine learning models. So these possibilities are encouraging partnership between the quantum companies and leaders in healthcare and AI to tackle big challenges in technology and health. Quantum computing is especially good at optimization, which means finding the best solution from many possibilities. So this can have big real world benefits. We can see in the slide also. It can be used for the different purposes, like smart cities. It improves the traffic flow, supply chains. We can make logistics faster and cheaper. And if we talk about finance, that is optimize investment portfolios, energy grids, that is balance sustainable energy efficiently. So because it can save money and improve performance, optimization is likely to be the first area uh, where the industries widely adopt quantum computing in the next 10 years. My next slide is the quantum computing. I named it the powering a sustainable future. So the quantum computing can help us tackle environmental challenges also. It can simulate the complex climate systems more accurately to guide better policies. If we talk about energy grids, it optimizes the renewable energies and use the efficiency. We talk about the material discovery. It speed up the development of the better batteries and the carbon capture technologies. by improving energy efficiency and helping us understand and solve environmental problems. The quantum computing can play a key role in building a sustainable future. This is the quantum compute. Just I have skipped this slide. Energy efficiency. I have covered all the 4 points. So the quantum industrial revolution. The quantum computing will transform industries, that is finance and healthcare, better risk analysis and fast drug discovery, manufacturing more efficient processes with less waste. If we talk about the cloud access, let us startups and researchers experiment, spreading innovation. So this will create a thriving ecosystems where companies and the universities collaborate, leading to a new business models and the valuable economic opportunities. This slide shows India's quantum leadership vision. So India is aiming to become a global leader in quantum technology through its national quantum mission. That is, India's national quantum mission focuses on the computing, communication, uh, and indigenous hardware development. And this mission focus on the building homegrown hardware, advancing quantum communications, and creating research centers across the country. And it supports academic research, startups, innovations also, and training, that is also include for the skilled workforce. So these various efforts aim to create a strong quantum ecosystems. Just a minute. Uh, so these efforts aim to create a strong quantum ecosystems, helping India benefits economically and scientifically from the upcoming quantum era. These are the high demand quantum carriers. So the quantum computing is creating exciting new job opportunities. The quantum revolution is creating many career opportunities across research, industry, and in the other domain also. So if we talk about the algorithm designers, it creates new quantum solutions. We talk about the hardware engineers, so it builds the quantum processors. Quantum AI researchers that develop AI using quantum computing. And if we talk about the software developers, make tools and programs for quantum machines. So these jobs need a mix of the physics, computer science, and specialized knowledge. So they offer a strong growth and competitive pay in the cutting edge field. Both government and the universities, I have just discussed in the earlier slide also, that both government and the universities can play a vital role or key role in advancing the quantum technology. If we talk about the government, they can provide the funding, create supportive policies, and encourages collaboration between public and the private sectors. If we talk about the various universities within India or outside India, they can train skilled quantum professionals. They can conduct the research, update courses for industry needs, and they can share the knowledge on various platforms. So the I mean to say that working together, they can ensure the long term success and help the country to stay globally competitive in quantum technology. My next slide shows the balancing challenges and opportunities. So the quantum computing faces big challenges like high cost and technical errors, which slow down short-term adoption. So, but the opportunities are huge, we can say. And the if we talk about faster computations and innovations across every industry, they could be truly transformative. So we can balance both of the things. The way forward is the invest in research and education now. So we can work together and solve problems step by step. So by doing this, we can overcome today's limitations and we can unlock the full potential of quantum computing to benefit the society. So this is my last slide. The quantum future awaits. So in conclusion, the quantum computing. If we see this slide, I have mentioned the powerful emerging technology that is quantum computing faces technical challenges in hardware, error corrections, and scalability, but steady progress continues. A strong government and industry support that is also required. So while challenges like fragile hardware and scaling up remains, the process is speeding up worldwide, and growing software and applications could transform society. But we must also consider ethics and the security also parallelly. So the possibilities are vast and exciting, and we are at the beginning of the new era in computing and ready to solve some humanity's biggest problems, we can say. So these are my outlooks in the quantum computing. I have prepared. I have tried my level best to prepare uh, or to justify the topic for the challenges and the future scope of the quantum computing. I'm just seeing the chat box.
Thank you so much, sir. There are some of the questions that are asked in chat box.
Just a minute. Not able to see the chat box. Just a
Rika
minute.
ma'am, please ask the questions. Read from chat box.
Just a minute. Just a minute, please. Just I'm stopping share my screen. Just a minute. Kanika, in my presentation, the slide was not in the full screen mode. Huh?
Sir, it was in the full screen mode. So maybe due to some network error, other people
Okay.
was facing that.
Okay. Dr. Sandeep. Sir, any possible collaborations with the RKGIT faculties in the era of quantum computing? Definitely, sir. We always welcome for the individual collaborations, for the university collaborations, and for different MOUs uh, in the field of quantum computing and in the other fields also. Just a minute.
Thank you so much, sir, for an exceptional session. Your discussion on the future trends and challenges in quantum computing has been both enlightening and inspiring. To our participants, we hope you have enjoyed this incredible journey over the past 6 days. Do not forget to fill out the feedback and attendance form for this session, which has been shared in the chat and WhatsApp group. Before proceeding further, I would like to draw the kind attention to all the participants to some important instructions regarding the Atal portal, which are essential for certification. Please note that an assessment test will be conducted on the Atal portal tomorrow as in today from 6:30 p.m. to 7:30 p.m. This assessment will consist of 25 MCQ type questions based on the topics covered during this FDP. After completing the assessment, all participants are required to fill out the feedback form on the Atal portal itself. The feedback link will be available just below the assessment link on the portal. Only after successfully completing the assessment and submitting the feedback form, and upon meeting all the eligibility criteria prescribed by the AICTE Atal Academy, Participants will be able to download their digital certificates directly from the Atal portal